Our year-long project is a necessary product to protect satellite payloads. During operation, a method of isolating vibrations is required to avoid negative effects on the functions of such payloads, such as sensors or cameras. A structurally sound damping assembly, which will withstand two main areas of operation, will prove to be the most effective. Our project has been designed for damping in two stages, which isolates vibrations at two distinct frequency ranges and loading cases.
Our sponsor, Maxar Technologies, provided us with a specific viscoelastic material to use for designing our project. We began the design process by brainstorming different methods of utilizing the viscoelastic material. Next, we created several conceptual designs before selecting our final design based on damping, stiffness, and structural analysis. Our final design consists of 3 pedestals attached to a flexure plate and associated payload. The viscoelastic material is located inside the rotating links, damping the motion of the payload in any axis. The pedestals are 2-stage vibration isolators, which change their natural frequency and damping based on passive contact during the satellite launch. The pedestals are made from primarily aluminum for its lightweight and machinability, and Garolite for its impact resistance. The 3 aluminum plates were designed to be CNC machined, while the remainder of the components are manually machinable or bought off the shelf.
Now I will talk about the block diagram for the pedestal. The program we are using to model the pedestal is Simulink, and within Simulink we are using a toolbox called Simscape. Simscape allows us to model the pedestal using masses, ideal translational springs, and ideal translational dampers. Additionally, we are able to model the input to the system as a base excited force, similar to how we would test a physical model with the shake table. Sensors placed throughout the model record position, velocity, and acceleration, allowing us to understand the system's response to a 0 to 100 Hz sine sweep. These values are particularly useful when we use MATLAB to process these results and plot them with respect to frequency to see transmissibility as well as resonant frequency.
FEA was used to verify that our design met the stiffness, also our first mode natural frequency, and the structural requirement. We used the modal analysis package in ANSYS to look at the first natural frequency of the system. 2 separate analyses were performed to look at the launch phase and orbit phase independently for model simplification. Model results also provided strain energy density, which was critical for our design. Since most of the damping in the system occurs at areas of highest strain energy, we were able to determine what areas needed additional stiffening as well as geometry modifications to relocate that strain energy. Other than modal, we also ran a structural analysis of our system to make sure our design met the structural requirements during worst-case loading condition. The 2 main loading cases we were concerned with was the 20G quasi-static load applied at the off axes and the launch load at maximum transmissibility. By breaking the system down into smaller components, FEA was a lot more manageable and provided quick turnarounds for certain parts that would be more prone to failure. Without FEA, we would not have been able to verify our MATLAB or Simscape models.
To validate the damping properties of our two-stage design, we drafted detailed testing procedures. The main testing procedure runs a sine sweep to validate that the designed assembly meets the natural frequency and transmissibility requirements for both launch and orbit. An offsetting shaft accounts for the non-zero gravity environment of the shake table. The next testing procedure compared damping and transmissibility values before and after testing to note any changes as a result of the loading. To test the quasi-static requirement of 20G in all axes, a weight is used to simulate static equivalent loading applied through the center of gravity. A shaft offsets the load at a specified distance from the flexure plate. These tests include tensile and compressive axial configurations as well as a horizontal orientation. Finally, we created an offloading testing procedure. Though not a primary requirement, this test accounts for the likelihood that the offset center of gravity of the payload attached to our system could alter damping effects. This test restricts one of 3 pedestals to the launch configuration and tests the resulting damping and natural frequency properties of the system. Next, we use the shake table to find the damping properties of our prototype VEM, FlexSeal, per ASTM E756, measuring vibration damping properties of materials. From this test, we were able to extract the shear modulus and damping coefficient of the FlexSeal using sandwich panel beams. We performed yet another test per ASTM D1002 adhesive lap joint shear testing, fixturing composite lap shear joints in an Instron. The tensile test results provided an approximate adhesive strength of our prototype VEM. Using the results of the FlexSeal tests, we were able to translate the shear strength of our prototype VEM to predict the shear strength of the actual VEM in our assembly.
The largest challenge to the project was the high stiffness of the specified viscoelastic material, which made it extremely difficult to achieve the transmissibility requirements while simultaneously meeting the natural frequency requirements of the project. While our project theoretically met the frequency requirement, according to our analysis, we were unable to achieve the transmissibility requirement with the chosen viscoelastic material. Unfortunately, we were unable to manufacture and test our pedestals to verify our analysis due to the COVID-19 situation. However, Maxar is planning to continue this project through a new team next year.